In this video, we are going to learn how we can use Python programming for solving ordinary differential equations. The ODEint function from the scipy.integrate module is capable of solving linear and nonlinear ordinary differential equations of any order. It can solve problems that are non-stiff as well as stiff. It can solve initial value problems as well as if you have a forcing function in the differential equation, it can tackle those problems as well. So let's see an example. Let's consider the second order differential equation for a simple pendulum. So of course we are not assuming anything here. We are writing the ordinary differential equation, the nonlinear ordinary differential equation for the system here. Here theta represents the angular position of the pendulum. So and B represents a frictional term that is denoting the air friction, and C is a term related to the angular velocity of the pendulum. These are both positive constants. So to solve this differential equation numerically using the ODEint function, we first need to convert this second order differential equation into two first order ordinary differential equations. And there is a standard way in which you can do this. So since we have a second order differential equation, it will be converted to two first order differential equations through two variables x1 and x2. We would assume x1 is equal to theta t and x2 is equal to theta dash t. So the first derivative of theta. So in this sense, x2 is x1 dash. All right. Now, if we replace these two variables x1 and x2 in the original differential equation, we see that theta double dash becomes x2 dash plus b theta dash becomes simply x2 plus c sine theta t simply becomes c sine x1. All right, so that's the differential equation, and this of course implies x2 is equal to minus bx2, x2 dash equal to minus bx2 minus c sine x1. All right, so this is the differential equation, and of course the other one is by definition. This is how we defined it. So x2 is equal to x1 dash. So these two differential equations, or rather this system of differential equations, are representing this original differential equation. Here, if theta is the angular velocity in this problem, angular position in this problem, then theta dash is representing the angular velocity. So x1 is representing the angular position, x2 is the angular velocity. Of course, if you are solving some other type of differential equation, these variables would probably have different physical meanings. All right. So again, you can so let's get to the programming part, and you can actually skip this portion, skip this one. I write this line to get the plots as SVG files, but if you don't want that, you can actually skip this line. So now the packages that we need to actually get this through are the NumPy package, the matplotlib package, and the ODEint function from inside scipy. We will be using NumPy for creating arrays. We will be using the matplotlib package for plotting, and of course ODEint for solving the differential equation. All right. So here is the most important part. This is how you actually define the differential equation itself through Python. You have to define it as a function. You can name it whatever you want, but it requires at least two input variables. One of them is the initial condition, another one is the independent variable. Okay. Then of course the initial value here, initial values especially in this one would be an array with two elements, and we are actually extracting this into x1 and x2. So those will be the initial results for x1 and x2. Right? And of course b and c are two constants, so let's put their values as well. So we are assuming b to be 0.25 and c to be 5 here in this example. And this is the most important part. See that we are defining x1 dot as x2, just like the way we derived it, and x2 dot will be equal to minus bx2 minus c sine x1. This is exactly how we actually got this as well. All right, so that way we have defined the differential equation. But once again, these do not have to be named like this. You can name it whatever you want. I have written it as x1 dot and x2 dot just so that it actually makes proper sense. But remember that this function that we have defined should return the derivatives, a list of the derivatives. So x1 dot and x2 dot should be returned by the function here. Of course, if you have a third order differential equation, then you would probably have x1, x2 and x3, and there this initial value condition, initial value should also have 3 elements, and those things will be that will be expanded into x1, x2 and x3, and this function, this will be defining x1 dot, x2 dot and x3 dot, and it will return x1 dot, x2 dot and x3 dot, right, and so on. Now for this example, we are assuming that the pendulum is initially almost vertical. Okay, almost. So the initial angular position is almost pi, slightly less than pi in fact, and the initially it is at rest, so the initial velocity is 0. All right. So with that assumption, we are writing the initial condition. So this is how you write the initial condition. So let's first of all run this, and this is how you write down the initial condition. So this is again a simple list. It could be a Python array as well, whatever. So this is again a simple list. All right. You can define it as NumPy array, whatever you want. All right, so that is representing x1 0, this is representing x2 0. All right, now if I want to solve this differential equation over a time interval, in this example I am choosing the time interval to be from 0 to 10, and we have to define how many points we want in the time interval. Let's say we want 1000 points. So this is how we use the NumPy linear space function, NumPy linspace, and we are starting from 0 ending up at 10, and we are choosing 1000 points, right? And then this is the point where we are actually solving the differential equation. So we are calling the ODEint function. We are passing in the name of the function through which we defined the system of the differential equations. Recall, we called it pendulum. So we are actually passing in the name of the function through which actually we defined the system of differential equations. We are passing in the array of the initial conditions. All right, here it's a list, but it will be converted to a NumPy array internally by this function. And T is the again the independent time array here. Okay, so these are the three things we need to pass into the ODEint function, and if we run this, it has actually solved it. Okay, of course it will return an array that has 2 columns, each column containing 1000 elements. Okay, the first column will have the solution for x1 and the second column will have the solution for x2. You can extract the individual columns like this. Okay, so the first column now has been extracted into x1, and the second column has been extracted into x2. All right, so again, so this is the solution for the angular position, and this will be the solution for the angular velocity. So now all that is left is to plot the results, and this is again standard and matplotlib, and if we plot the result, we see that yes, indeed, we have a proper solution here. So that's the end of this discussion. Thank you very much.